concept which comes is calorimetry. Whenever phase changes are involved, a solid turns into a liquid, or a liquid solidifies into a solid, or a solid evaporates into a gas. Solve the problem in 2 steps. For example, if heat is lost in a system is given to another substance in a different phase, first find the amount of heat required for the substance to change phase. Then use that calculated quantity to solve accordingly and find the equilibrium conditions. Thermodynamics has 3 laws, actually 4. The 0th law of thermodynamics states that when you have 3 bodies A, B and C, and A and B are in thermal equilibrium with each other, that is, there is no heat flow between them, and B or C are in thermal equilibrium with each other, then A and C will also be in thermal equilibrium. That is, thermal equilibrium is transitive. This allows us to define a scale of temperature. The first law of thermodynamics is the most important and relevant for us in physics. It essentially says that the heat given to a system is equal to the work done by the system and the change in internal energy of the system. Intuitively, you can understand this as follows. By giving heat to a system, we are giving energy to the system. We are doing a sort of work on the system. And this is used either by the system in doing its own work, or is used by the system to store in internal energy. The second law of thermodynamics says that entropy always increases. But it's not very relevant to us in physics. You'd study it a lot more in chemistry. Engine cycles and questions relating to graphs are important. Remember about the values of Cp and Cv. That is the coefficients when a process is done under constant pressure or under constant volume, and the work that is done in these processes. Questions are by and large based on a thermodynamic cycle. That is, various processes will be done. One may be adiabatic, the next isothermal, and so on, until we get back to the original state. What we have to see is how much work has been done and how much work has been extracted out of the system in this heat cycle. Speed is of the essence in these kinds of questions. To enhance your speed, try and solve as many questions as possible that are based on the various graphs of thermodynamic processes. Remember that the equation PV equal to nRT is applicable in all cases. Here P, of course, is the pressure, V the volume, N the number of moles, R the constant, and T temperature. Also remember a common error when transferring from log of base E to log of base 10, multiply by 2.303. Don't lose marks for silly mistakes. In solving these questions, first of all, find out which parameters are increasing, which are decreasing, which are remaining constant. Remember, of course, when the work done of the system is positive, then the internal energy of the system increases. Some of the common issues that come up in thermal properties of matter. Issues related to heat flow. We have the standard equation for rate of heat flow, which is applicable in all these questions. Keep in mind its proportionalities. Always remember, solve all these questions in the Kelvin scale, because the equations are only applicable in that scale. Practice the problems that involve heat transfer. Remember that there are many equations that are derived from the original equation based on certain approximations. For instance, Newton's formula is based on a particular approximation that the temperature differences are small, say less than 10% or so. Properly understand the meanings of the various terms A, E, E naught, A naught, etc. Identify the process taking place, whether it is conduction, convection, or radiation. In thermal physics, which encompasses all of this that I've spoken about, we have heat transfer. It relates to the conductivity of materials, how susceptible they are to transfer heat, equilibrium conditions, heat transfers across infinitesimal elements, and their integration over the entire whole system. The various thermodynamic processes and cycles. They may be adiabatic, isothermal, isochoric, reversible or irreversible, where different things remain constant and different quantities remain conserved. Also radiation, absorption, reflection, etc. A lot of the questions on heat conductivity have direct analogies with electrical circuits. So if you know how to apply Kirchhoff's laws and solve electrical circuits, then you'd find these some similar in that you'd have rods in series or rods in parallel. Questions of assertion and reasoning type are often asked based on these kinds of concepts of black bodies, emissivity, etc. So make sure that your concepts are completely clear. Also we have heat concepts and calorimetry. Modern physics. The term modern physics, taken literally, means of course the sum total of knowledge under the head of present day physics. In this sense, the physics of even 1890 is still modern. Very few statements made in a good physics test of 1890 would need to today be deleted as untrue. The principal changes required would be in a few generalizations, perhaps to which exceptions have since been discovered, and maybe in certain speculative theories, such as that concerning ether, which any good physics of 1890 would have recognized to be open to possible doubt. On the other hand, since 1890, there have been enormous advances in physics, and some of these advances have brought into question and in fact even directly contradicted certain theories that seemed to be at that time very strongly supported by experimental evidence. So where are problems asked from this chapter, and what are they generally based upon? There are different concepts. A lot of them are based upon the photoelectric effect and the experiments conducted by Einstein. In fact, his Nobel Prize is in fact based on his 1905 paper. The binding energy that is required to release electrons from the surface of a particular metal. By and large, these are formula-based questions. Solve a lot of objective questions so that you're prepared for questions from these chapters. Remember, modern physics is a new subject. It's not very well known. It's not very simple either. A lot of things will be told to you in this chapter without the rigorous analysis that was there, say, in a mechanics or optics or thermodynamics or electricity. Don't go into the proofs of highly advanced concepts. They are neither relevant to the JEE nor within the scope of our comprehension now. Accept the basic fundamental principles and build upon that. Modern physics deals with the dual nature of radiation and matter. Some of the common doubts are in the photoelectric effect. Understanding this dual nature. How are X-rays formed? What is their intensity curve and distribution? To understand this, we should remember that wave nature and particle nature are not simultaneously. What is the photoelectric effect? One photon can interact only with one electron of a target at one particular time. Whereas classical theory assumes that wave continuously accumulates energy over the target electron when the electron is removed. This can be proven wrong by certain very standard experiments and the consequences that we expect from this discrete and continuous thing. Read the theory. Then we have Bohr's model of the hydrogen atom. Using that particular model, we deal with the hydrogen spectra. We can't see the color of the electromagnetic spectra, but a set of discrete wavelengths in absorption or emission spectrum are present because the process is quantized and not continuous. The number of emissions when an electron jumps from one level to another is a factor that we often have to consider or calculate. Remember the formulae well. Also, understand the concept of ionization energy. It is the energy required for an electron to jump from a given n shell to n is equal to infinity. That is, to escape the hold of the nucleus. The concept of X-rays. They can be produced in two ways, giving rise to two different distinct kinds of X-rays, either continuous X-rays or characteristic X-rays. Make sure that you understand and know what Moseley's law is and where it's applicable to. In the graph, the peaks are superimposed of the continuous as well as the characteristic X-rays. The intensity is high for the characteristic part because the energy of the incident electrons is distributed only over a few discrete wavelengths. However, for continuous, the energy is distributed over large range of wavelengths. The atomic nuclei, binding energy curves, mass defect concept, and the processes of fission and fusion, and the various energy conservation questions that come into play should be well understood. Binding energy is the amount of energy that must be supplied to the nucleus to separate the constituent nucleons to large distances away from each other. Nuclear fission and fusion concept relating to the BE curve. What is fission? When a heavier element having a lesser binding energy per nucleon splits into a middle-sized nuclei, the effective binding energy per nucleon increases. Therefore, energy is released in fission. Remember, this deals with heavy nuclei breaking into lighter nuclei which are still middle-sized and have a higher binding energy. What is